will change. So we go to the next example. And that's then the last example in this section. So now we take the matrix A, which is equal to 3, 6, -1, 0, 3, 0, 0, 5, 2. So pretty simple. It's not too difficult to find here the eigenvectors and eigenvalues. So you have here one column with only one number and here one row. So actually it's pretty simple to find here the eigenvalues. So let's start with this. So we have 0 equal to the characteristic polynomial, which is equal to determinant. First I write like this, lambda I minus a, which is the determinant of lambda minus 3 minus 6, 1, 0, lambda minus 3, 0, 0, minus 5, lambda minus 2. And now, as I said, you can either pick column 1 or row 2. What did I do? I used, for whatever reason, row 2, but it really doesn't matter. Row 2, so I use this plus minus plus, so it's lambda minus 3. Determinant of, so I delete row 2, column 2. I have lambda minus 3, 1, 0, lambda minus 2. And we see, oh, that's perfect. No, lambda minus 3 times this, lambda minus 3 times lambda minus 2 minus this times this. So I didn't even write here. So we are done. No? So right away out of this comes a factorization of the characteristic polynomial. So we have our eigen. Oh, okay. I could also write one more combination. So I combine these two. So what are the eigenvalues? Of this matrix? What are the zeros? The zeros are
3 and 2.
3 and 2. So I make lambda 1 equal to 2 because it's a smaller one, I guess. Lambda 2 equal to 3. And when you look at the algebraic multiplicity, what is the algebraic multiplicity of 2? How often is 2 a 0?
Only 1.
Would be 1, because here's exponent 1, and 3 has algebraic multiplicity
Of 2.
2, no? Because here the exponent is 2. And from the equation I showed you now before, actually we have not proved this, but this is what's true. So we know for lambda 1 equal to 2, we have 1 larger or equal to the geometric multiplicity larger or equal to 1. And for lambda 2 equal to 3, we have 2 larger or equal to the geometric multiplicity larger or equal to 1. So right away, what can we have to say about the geometric multiplicity of the eigenvector 2? Which number can it be only?
1.
Yeah, because it's a number between 1 and 1. So there's, let's make here the geometric multiplicity is 1 for lambda 1 equal to 2. And what about lambda 2 equal to 3? 2 larger than the geometric multiplicity, larger or equal to 1. So what kind of options do you have for 2? For also lambda 2 equal to 3. The geometric multiplicity can be
2 or 1.
2 or 1. No? Also I write 1 or 2. In the previous example, it was 2, no? Because the geometric multiplicity was also 2. But in theory, it can be 1 or 2. Okay, as you can imagine, this is now an example where the lower number comes out. No? Okay, so how do we find the geometric multiplicity? We find the eigenspace and see how big the basis is. No? Okay, again, I need to go to another paper. So this is our matrix. This is always what I take, and now I plug in for lambda 2 and I plug in for lambda 3 and then solve equal to 0. So I take always this and plug in my 2 lambdas. So now we find the eigenvectors. So now we go to eigenvectors. So lambda 1 equal to 2. Again, I take this matrix, put a lambda equal to 2, and the right-hand side is 0. So I copy this with lambda equal to 2. I get -1, -6, 1, 0, -1, 0, 0, -5, 0, 0, 0, 0. So this is what I get here for 2. And again, I turn this here into my leading 1. So I multiply by -1. This here also I multiply already by -1. So that will be another leading 1. And this here I eliminate right away, -5 times row 2. This turns into 1, 6, -1, 0. This times -1, 0, 1, 0, 0. This plus 5, -5 times this is 0, 0, 0, 0. We have our 0 row. So we know that's a good sign. That means our calculation of the eigenvalue seems to be have been correct. The last thing is this is row echelon form. We reduce by putting the 6 to 0. So I make -6 times row 2. So I have 1, 0, -1, 0. 0, 1, 0, 0, 0, 0, 0, 0. Again, 2 leading 1s. So C gets a parameter if I have here x, y, z. So C is equal to T, T in R. Then we have y equal to 0. And x minus comes over is also T. So the solutions would be T times 1, 0, 1. T in R. Eigenvectors we only get for T not equal to 0. So I put T equal to 1 and I have my first eigenvector 1, 0, 1. So this is the eigenvector for 2. Okay, now we go to the second eigenvector, which was, what was it again? 3. So lambda 2 equal to 3 had algebraic multiplicity 2. So again, I take this matrix, instead of lambda, I put a 3. So I put 0, -6, 1, 0, 0, 0, 0, 0, and then we have 0, -5, 1, 0. So this is what we get. And okay, the first column is totally 0. We no way that we get a leading 1 here. So this is already done. So what I can do, for example, is I can put this to 1. And so I divide here by -6. And here I subtract 5, 6 times row 1. So this is 0, 1, -1, 6, 0, 0, 0, 0, 0. Okay, I should have also switched, but I forgot. And this -5, 6 times this is 0, 0. And then 1 -5, 6 times this is 1 -5, 6 is 1, 6. And 0. Then I multiply this by 6 and I switch. So I get 0, 0, 1, negative 1, 6, and 0, 0, 0, 1, 0, 0, 0, 0, 0. This is row echelon form. In the final step, I make this equal to 0. So plus 1, 6, row 2. So if 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So obviously, this and this are leading ones. So x get a parameter. X is equal to t. Once I have this, it tells me y is equal to 0, c is equal to 0. So we have t times 1, 0, 0. So an eigenvector, again, for t equal to 1, we get 1, 0, 0. So keep in mind, 3 had algebraic multiplicity 2, but we find only one eigenvector. So the geometric multiplicity is 1. So it's actually less than the algebraic multiplicity. So again, we write this down. So the eigenspace for eigenvalue 2 is the span of V1. So the dimension of E2 is 1 because one vector generates it. The basis has one element. And that means the geometric multiplicity is also 1 because geometric multiplicity is another name for the dimension of the eigenspace. And then the same with E3 is the span of V2. So the dimension of the eigenspace for 3 is 1. And again, that means the geometric multiplicity is 1. So from the two options we wrote down here, so we know this is 1. That's exactly what we found. And from the two options we had for the eigenvector 3, eigenvalue 3, it turns out it's also the 1 and not the 2. So it turns out this matrix looks very simple, but it turns out you cannot diagonalize this matrix because you don't find 3 eigenvectors. You only find 2. So this matrix cannot be transformed into a diagonal matrix because transforming into a diagonal matrix means you have a basis of R3 of eigenvectors. But this matrix has only 2 eigenvectors, or let's say here, V1 and V2. It doesn't have 3. So not every matrix can be transformed into a diagonal matrix. And this matrix is an example. Okay, that is kind of bad news because until now, this whole section was always a little bit, oh, we find 3 eigenvalues, we find 3 eigenvectors, or we find 2 eigenvalues, one is double, one is single, we find 3 eigenvectors, one for the double and one for the other. So this matrix destroys our hope. So we cannot always bring every matrix into diagonal shape. And this matrix is our first counterexample. So yeah, that's kind of bad news, no? So not every matrix can be transformed to diagonal matrix. So the question is there anything else we can do with matrices like this, no? And it turns out, yes, there is something. And that's, I like to just show you in an example now. And I continue with this example. So the question is, what can we do to simplify the the representation of this matrix. Obviously, we cannot bring it into diagonal form because then we would need 3 eigenvectors, and this thing has no 3 eigenvectors. No, it was only 2. Okay, and it has something to do with the eigenvector 3, because here we have 2 algebraic, but only 1 geometric. So here is kind of a gap. No? So we have 2 here, but only 1 here. So isn't there something else? Because apparently there's something missing here. No? And it turns out, yes, there is something else. And so we continue with the 3. No? So, and we go back to, how did we actually found V2? Oh yeah, we solved the equation 3 minus a equal to 0. No? So I write this down on the next page. So we have 3 times the identity minus a times V2 is the 0 vector. No? So that's actually how we got V2. We have a homogeneous system, and that's how we got this. Okay, and now I don't know really how historically, how someone got this great idea, but somewhere around, it's actually not too long ago, maybe 120, 150 years at most, someone had the idea, okay, so there's no eigenvector, but maybe what we can do is, instead of solving 3i minus a times x equal to 0, that's how we found V2. We do 3a minus a squared times x equal to 0. For sure, this is a vector we find again, because if you apply the matrix once, it's already 0, so you don't have to apply it twice. So this is essentially an iteration of the matrix. So you do it, instead of doing it once, you do it twice. So the first thing is we have to find this matrix. So 3i minus a, remember from here, was, okay, I just copy it, 0, minus 6, 1, 0, 0, 0, 0, negative 5, 1. So now we have to calculate the square of this matrix. So I multiply it out. And let's see that we don't make any mistake. The first column is clearly a 0. Then minus 6, negative 5, 0, minus 6, negative 5. And then 1, 1 means we add first and last column, 1, 0, 1. Okay, so this is our 3i minus a squared. So now we solve the homogeneous system again. So we write 0, negative 5, 1, 0, 0, 0, 0, 0, 0, minus 5, 1, 0. And oh, that's easy now. So we divide here by negative 5. We subtract row 1. And we are done. This is our reduced row echelon form. So if we have x, y, and c, y is the leading one, x and c get parameters. So x is equal to s, y is, c is equal to t. S and t in R. And then y, I bring this over here, is 1/5 c, so it's t over 5. So the solutions are x, y, c is equal, so it's s, t, t over 5, which is the same as s times 1, 0, 0, plus t times 0, 1/5, 1. So we get two vectors. V1 is when you set s equal to 1 and t equal to 0. So you get 1, 0, 0. And then you get, oh sorry, this is V2. And then we get V3, which is, I put t equal to 5 just to get rid of my fraction. I get 0, 5, no, 0, 1, and 5. No? So this is s equal to 1, t0. This is s0, t5. Okay, so it turns out this is the same vector we found here. So that's not a surprise, because if you apply the matrix once, it's already 0. So for sure, if you apply the matrix twice, it's 0. So that we found V2 again, it's not a surprise. The surprise is we find another vector, 0, 1, 5. So this is not an eigenvector. Otherwise, we would have found it before already. So this is actually a 0 of 3i minus a squared. So you have to apply the matrix twice to make it 0 instead of once. And so this is an example of what's called a generalized eigenvector. So it's not an eigenvector, but it's called a generalized eigenvector. It means you have to apply this matrix maybe several times. In our times, good thing, only twice. No? So this is an example of a generalized eigenvector. This is an eigenvector. Remember, we found this before, but this is not. But if I apply the matrix twice, I get a 0. Okay, now what happens now if we made, and obviously these are linear independent, so I can make the matrix with V1, V2, and V3. So like before, we make our matrix P, V1, V2, V3, and again, eigenvector, eigenvector, generalized eigenvector. And so this is the matrix 1, 0, 1, 1, 0, 0, 0, 1, 5. Then you can calculate P inverse, which if you do this, you get this matrix. And now the big question is, what about if we multiply this and this with our matrix A? So the big question is now, what does all this actually teach us? Okay, and it starts really good, like what we expect. This is the eigenvector for 2. So there's a 2, 0, 0. Very good. This is the eigenvector for 3. So there is a 3. And this is a generalized eigenvector for 3. It turns out we are lucky. This is a 3 too. But now comes the new thing, because we know that cannot be true. Because if there would be 0 here, we would have 3 eigenvectors, and that's impossible. It turns out now we get a 1 here. So this matrix A is an example which we cannot transform to diagonal form, but we get something along the diagonals are the eigenvalues, but on top there's a possibility of getting 1s. And this indicates the third eigenvector is not an eigenvector, it's actually generalized eigenvector. Yeah. Okay. So, and what can we say? What is this block actually? Keep in mind, so this is 3, 1, 0, 3, which is can also be written as, I factor the 3, it's 1, 0, 1, 1/3. And it turns out this is not a stretching or a shrinking, this is a shear. So this is a shear matrix. Okay, and this thing again, it's not a diagonal matrix. So matrices which have the eigenvalues on top and then 1s on the super diagonal on the next line, this is what we call Jordan blocks. So this is an example of a Jordan block. And now you can say, but okay, this was accidentally just in this example. Maybe that doesn't work always. It turns out it works always. So every matrix, we can always find a basis of generalized eigenvectors such that P inverse AP is a diagonal matrix where along the diagonal are all the eigenvalues, and some of them have ones on top. So these are shear matrices. So every matrix can be written in a special coordinate system as a combination of diagonal matrices and shear matrices. And that's a pretty deep result. Although there's no way, even if you give me another 15 weeks, we might not be able to prove this, but that is something which turns out to be true. So for every matrix A, n by n, we can find generalized eigenvectors v1 to vn. Then we make the matrix P, which is the matrix of these columns, and P inverse, then P inverse A times P is a matrix where we have blocks along the diagonal. So let's say J1, J2, J3, J4, and so on, where each J has either the following shape. It's either a diagonal matrix, only eigenvalues, or, okay, sorry, I have to switch to the next page, or J looks like lambda along the diagonal, 0 down here, and 1s on top, and 0 up here. Yeah, so each thing along the diagonal either has eigenvalues along the diagonal, that's what we have seen until now, or it has eigenvalues along the diagonal and 1s on top. And every matrix can be written like this. That's kind of the amazing part again. So every matrix, if you find the right coordinate system, is built up of 3 different things. It's stretching or shrinking, reflection, that's a negative eigenvalue, or you have 1s on top of the diagonal, which means it's shears. Yeah. Okay, so that is something that is kind of amazing. So no matter what matrix you pick, if you look at it in the right way, it's made out of these 3 things: reflections, stretching and shrinking, and shears.
Professor?
Yeah?
What does it say for the second to last matrix on the other page?
Here?
The other one? To the left? Like, what does it say across the diagonal? Is that...
Oh, this one?
Yeah.
Oh, this is capital J1, capital J2. Okay, maybe I should try to.
Oh, J?
It's, yeah, just capital J's, no? So this is capital J1, capital J2, capital J3, dot, dot, dot. And I don't know how many there are, no?
Okay.
And when I say this, it means outside is always everything is 0, no?
Mm-hmm.
And each of these guys is either a diagonal matrix with eigenvalues or diagonal matrix with eigenvalues plus a 1 on top.
Okay, thank you.
Mm-hmm. So that means every matrix can be written in this form. Okay, so yeah, I think there's no point anymore for me to start section 6.1. So 6.1 will we start tomorrow, which now switches to essentially to dot product again. Remember dot product we get in chapter 3. 3. We did the dot product. And in chapter 6, we generalize the dot product for general vector spaces. So the dot product is our blueprint, and we make it more general, and then it's called an inner product. And so this is what we do for the last 2 days in this class. We talk about inner products, and that starts tomorrow. But also keep in mind, so you really see that things getting more kind of complicated, but also keep in mind these things, what I just told you about the Jordan blocks, that is not in that's not in the book, and you will not ask about, but that's kind of the bigger picture here, no? So people were thinking every matrix, if we try to simplify, how much can we simplify matrices, no? And you can say, what does simple mean? Simple means like a diagonal matrix, no? And it turns out they early on found out not every matrix can be written as a diagonal matrix in the correct coordinate system, but if you use a suitable, let's say instead of correct, say a good coordinate system, the matrix becomes simpler in the way it's either diagonal or diagonal plus a line of ones. And the interpretation of the ones is like we had the geometrical interpretation, I think it was section 6, 4.9. The interpretation is it's a shear. And for sure there are shears, because that's what they found out in mechanical engineering from the beginning, that there are shears. But shears cannot be brought to diagonal form. So that's here the message. No? Okay, so this finishes 5.2. So later on there will be homework for 5.2. And tomorrow I continue with 6.1. And then on Wednesday, I think we finish off with 6.2 as far as I can go. The 6.1 and 6.2, both are kind of long sections. I'm not even sure how far I can go, but definitely 6.1 will be on the final exam also. At least let's say one question or something like this. Okay, I hope I remember this. I will also post later a list of sections which can be on the final exam, but in some sense the short version is everything we did in chapter 4, 5, and 6. No? That will be for the final exam on Thursday. With the majority, because that's also when you think back where we spent the most time, the majority will be chapter 4. Okay, any more questions? I hope that was not too. Okay, any more question about this? Otherwise, I see you either at 3 for office hours or tomorrow for our next lecture. Any more questions? Okay, then I stop sharing my screen and I finish the Zoom meeting. See you later or tomorrow.